Hello, and welcome to another later issue or episode, issuance of Descriptive Differential Dynamics. It's November 19th, 2023. So after a hiatus of some few months, I stopped to think about the stop derivative and the idea how it reflects the sort of complementary dual of the usual notion of the derivative, but also the usual notion of things in terms of velocity and continuous motion and such as usually expressed in meters per second. What it means in terms of the opposite and the complement. What is seconds per meter, or this stopping distance is the idea, is why it's called the stop derivative. And then I haven't really put much thought into it, since then. It's just kind of an idea. It's an idea fix that it's something that deserves its own attention as part of the system of all the complementary duals that implement such manners of things as classical motion. But with respect to such talks as the talks on Einstein and Einstein's attack on Newton's classical motion and for the total field theory and the Machian and this kind of thing, and then after and above, the studying of the second course in differential dynamics, or a second course in differential equations, and this kind of thing is hoping to get into a sort of starting place where various of these notions of the related terms, quantities, properties, tendencies, and propensities of the restitution, oscillation, attenuation, and dissipation, and some of these other notions of these phrases or words invented to name these things over the course of the issuance of the, how you might say, study so far related in these talks over these times, that what I've arrived at is not so much more since then. At the same time, though, it's kind of settled and been settling in terms of this consideration of this idea fix of the identity dimension and what that relates to make what it is possible to consider about what goes into setting up the abscissa and the ordinates and the coordinate space and the coordinate settings and the framing of, for matters of perspective and projection, what we can see to arrive at these ways to place them together is for making, for the original sort of analysis and the Cartesian sort of analysis, and of course our Euclidean geometry and this kind of thing, trying to figure out how to get to these wider concerns, and then to help reflect for what is usually the entire consideration of classical quantities as under conservation laws and the conservation of various conserved quantities, energy usually, momentum, that these days it's even kind of beginning to be understood in a wider world, or being more investigated, the ideas that something like momentum, generally considered a conserved quantity, is actually of a world of the pseudo-momentum, that the Nessie's hump, or the difference between the angular and the linear, and the kinetic and kinematic, and the ideas that the momentum is not really a conserved quantity, that pseudo-momentum is a thing. So you can find this, you can discover this the wiki or in the internet, or as you may research, hopefully at some kind of well-equipped university library, or in the course of the halls and the studies, that it's possible to get an idea that some of these things that were considered classical and viable, after causality, which some people have as the inviolable of our theory, others thinking that it's just a stochastic statistical world, when this can be left off as that they don't have access to a superclassical milieu where the resonance theory adds up for these notions of how space-time is a continuous manifold, yet we must have this Galilean invariance and Lorentzian invariance, and how it results as sort of a quasi-invariance, that it makes for this notions of like the pseudo-momentum, that these ideas of the meeting and parting and starting and stopping and the frames for theory overall and writ large is, again, here is for the usual idea that the goal is to help reflect that Newton's and Einstein's theories grow and find that their potential is fulfilled. The potential is the potentiality, or what could be possibilities in their likelihoods, that it works out that the potentials are the real part of the fields, and the classical part we have and the linear impulses make for that it's not all the assumptions that we generally hold true in those settings are actual and real. So this is, again, just kind of a recapitulation of many of these ideas that have come up in these earlier talks about how to try to figure out what is these contributions that go into trying to improve, and also to provide for this deconstructive account underneath the what are considered the quantities, how these pseudo quantities, these degenerate quantities, the quasi quantities, are these real things. So while I haven't been recording any videos, I still try to collect books every day and read a little bit more. And so some of these, what I've been studying is much of I've been reading about classical theories of energy and the entelechia, which is connectedness and completion since the ancient Greeks or whatever. That this time and place of the 500 plus year span when the thinkers of the time made their cases for reason and for their deconstructive accounts of all things elementarily, that studying the energia, dynamism in its own form, or the potential for action, in a sense, potential to do work. And then the entelechia is another thing that then speaks to what we have in our current day as connectedness and these completions, that any time of these places where we have the inductive impasse about what can be reached, and then the deductive inference that allows the meeting in the middle of nowhere, as was discussed, makes for why some of these classical concepts, and that they're richer in a sense sometimes than what we've received of them as the wisdom today, that gets into why there's been some of the readings of the classical theories, Pythagoras's and Plato's, and after the Eleatics and Heraclitus and the obscure and this kind of stuff, gets into why that this study and this, I figure, will be useful and fruitful, because I can always pick up and put down those terms because they've been saying for thousands of years. It's part of the canon. It's part of the underexplored canon. It's part of the canon that is applicable because it's part of the reasoning apparatus and what results to things. While at the same time, it's to be refigured how it attaches to the fixtures of all the usual modern apparatus of formal systems. So I've been reading Heidegger. He's a philosopher, and he kind of is the torchbearer or poster child, as you will, of the German tradition, or Göttingen, and that Kant, Hegel, Heidegger, being nothing in time, and then he talks about Dasein and or the being here, and that time though is really the notion of this continuous quantity. After being in time, it's basically what fills in the middle is this kind of concept. And so I learned that he is most famous for that, and then afterwards mostly for translating and writing out the Greeks, and for Parmenides and Pythagoras and Plato, and that he basically just reuses all them, and so that's why he's perceived to be kind of the inheritor of that, and then after him to his student Gadamard or whatever, as basically, then after Husserl and into Habermas and these kinds of things that get into the non-technical philosophy, which are still yet as parts of these ethics and morals, because philosophy is all manners of reason and belief and ontological commitment to things. That then also I've been reading quite a bit of Bohm, Dave Bohm, and it's Bohm, and he's most familiar as with regards to Bohm de Broglie, and then also later on, and he's quite long-lived, and about the quantum mechanics and the theories and the ideas and the issues that go in the quantum mechanics and atomism, or Democritan, or after Democrites' theory of atomism, and what's connectedness and what's cutting the connectedness, and what are connected domains and these kinds of things for continuous domains, and then what are these notions of the degenerate, the pseudo, and the quasi that makes for the inductive inference either way, from something that is completely connected to be entirely cut, or something that's entirely cut to be completely connected, that they reflect the same kind of necessary attachment to a least Kantian sublime noumenal infinity that is again just kind of recapitulating that these are these notions that have arise here as being the least and the most necessary ontological commitment to aspects of theory that can possibly at all be universal and true, and these kinds of notions about then whether or not we can approach these as our own limited milieu of shared reasoning, that we can still consider that it's above us, all around us, or universal in its usual aspects. So Bohm is quite good. And then he gets into notions like the quantum consciousness, or what does that mean about the mysterious, and these kinds of things, flights of fancy, as it were. Again, these aren't necessarily the attachments that are kept, while at the same time gleaning from a generous reading what are his important insights into the theories, and especially his way to help illustrate the concepts that are counterpoints to each other, that counteract and are counterexamples to each other, how they arrive at being their usual kind of dialectic, and the square of opposition, and the dialectic, and the strong thing. Then one other book or series I acquired was from Courant, 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 Courant. He's a pretty great student, a professor of differential equations, and so I got his books, differential and integral equations, and I've been reading those, or I leafed through and read those. Those are really greatly and eminently readable. I mean, for something like these university mathematics texts, and then this Courant, it really gets to where that it provides a lot of the necessary background, and a very solid and good reading into the differential equations, and what those are, and why the ubiquitous success of mathematics in something that Einstein calls a total field theory of a differential system of all the quantities that live on a continuous manifold, for a unified field theory, for a grand unified theory, for quantum theory and relativity and all such manners of physics together. How then, as we get back down from that, of the notions of the strong nuclear force with its asymptotic freedom, and the very small being the same thing as quantum gravity, so that the strong nuclear force and the weak nuclear force sit together, and the electrical force and charge and the electroweak sit together, and so we have this tripos of charge and the kinetic and the transmutation of elements or nuclear forces and their dynamics and their statics. They're very long-lived, vis-a-vis that which happens at an instant. That then the idea is, again, to try to arrive at from least reasoning principles first principles to their final cause, and these universals from emptiness and nothing are the fundamental questions of metaphysics to arrive at this kind of thing. So with that, then, as been studying kind of just a second course of differential equations, and then trying to figure out the, how you might say, possible ways to find some improvements or some paths that help solve some of these things, where there's this notion of these talks of the symmetries, submersions, and sheaves as providing closed forms in algebra, or making limitations in the definitions for the submersions in this differential geometry, and then for this topology and function theory, and how that's redefinable, or what needs happen to make it so defined. These things these are the kinds of things that get into what could help to improve the notions of the integral curves and the differential equations for their plane curves and their solutions, to figure out for the linear, and then for the superposition of solutions, and then its sums of solutions are solutions in the linear, and this kind of thing. So for the various notions of what does it mean for something to be linear or nonlinear, and it was with regards to asymptotes and the singularity theories, which is here is discussed, are that any singularity theory is really a multiplicity theory waiting to happen, or simply some principal branch of otherwise a multiplicity theory. And the objects of mathematics, which fundamentally then are deconstructible in any such manner as they can possibly be, in as so far as they are. So let's take a look at some of these for a moment and see what we might find. So here, well, this is from before. The desk hasn't really moved too much since I was last sitting here. And so Kant's first critique, reflections on Kant's critique of pure reason. So this is Bohm and McIntosh. They're studying Kant. What I got from Kant a couple months ago was this critique of judgment. So after Kant, it came up with his early concepts after Leibniz and the tradition, and after Descartes, and then he came up with his critiques. And so my favorite one so far is his last one. So he's got three critiques, and the last one is the critique of judgment. And so it's a critique of aesthetic judgment and a critique of reasoning or teleological judgment. And so it basically gets into what is his desiderata and requirements of a theory of reasoning and the objects, therefore, that can be well defined. And if there's one takeaway from that, it's the sublime. The notion that Kant basically says that there's at least one aspect of the noumenon that's real and is subject to our object sense, the mathematical sense of an infinity, which we can never make phenomenologically real because we don't have enough fingers to count because they're finite. But the notion that there really is this the infinitely divisible, or the solutions to these paradoxes in this manner, Kant left that in his work as what is to be then picked up, so that you can see that it falls what on the other side was the noumenological and unavailable the phenomenological, and otherwise was the phenomenological and immaterial, even though it's only all material to us, but it's not relevant to all the noumenological, that is right there in the middle, and it's exactly and only that abstract kind of thing that is the thing that is there. So this is just some study of that, and then we got here, what is it, Nietzsche, Heidegger, and Taoist thought. Now this is pretty good because it gets into Taoism, and I'm not a big fan of Nietzsche anymore, and he's familiar with these things like will to power, because there's all these kinds of wills, and they're not necessarily all about, well, let's keep our inhibitions and get rich, or let's, have this notion that we can find philosophically any need for an ontological commitment to something that provides an aspect of a basis of free will, when otherwise that's already available. But at the same time, this is a pretty good book. And what is this here? Otto Frisch. Now, this was enjoyable. Otto Frisch, after they had the movie about like Oppenheimer and stuff like that, and the early people involved with the atom bomb, and such notions of the nuclear age, the atomic age. Otto Frisch is pretty cool, and so I read this, and one thing about it was that he talks about Stern-Gerlach, and what else we got in here? Wolfgang Pauli. Here's a picture of Wolfgang Pauli lighting his pipe, and the existence of the neutrino, which he proposed in 1930, was ultimately clinched in 1956. So Pauli and Dirac are both famous for coming up with a lot of different things that mathematically they showed exist, and then later they showed physically exist. Now, this is after the world of electron physics, which is a particle theory and discrete and finite and all that, after the ultraviolet catastrophe, when really it still had to come back that it's a wave theory, it's continuous and so on. That is conceit to that, how that may well be. That's still the Pauli principle that particles are indistinct and yet apart, and then Dirac with a positronic C, the vacuum field fluctuations, both have been shown to be true, and so that's pretty good. So this was pretty interesting. Talks about Wilson's cloud chamber and the fact that a lot of the different configurations and experiments, configurations and energies of experiments that ended up showing things like, as for Thomson and de Broglie and electron physics, can be redone at higher energy and configurations of experiment, and that they may well advise the real features of these particle wave dualities and these things that go into real physics without needing billions of dollars in a giant superconducting supercollider and a ring cyclotron or a linear accelerator like the Stanford Linear Accelerator. It's just to point out that Weber bars and Wilson's cloud chambers and stuff like that could be redone in a lot of different ways, vis-a-vis Millikan and these kinds of things. So this amused me because, and it's kind of like when Feynman talks about things. He says Niels Bohr got in touch with statesmen such as Churchill and Roosevelt. We try to convince the principles of the atomic bomb should be made public. Well, Pauli and Dirac. Penny Perels, John Cockcroft. So yeah, I enjoyed this book, reading about Otto Frisch a little bit. What's this here? Oh, this is good. This is the equations from God. I talked about this. And this is this fellow, Daniel Cohen. He talks about De Morgan and Boole and when symbolic logic came up. And Boole's pretty much facile with his symbolic logic. And he gets into one thing that I don't agree with, and that's basically it's one of these nothing and something things. So he takes a vacuous turn, and he ends up getting that he's kind of like the wellspring of what they call classical logic today. But classical logic, what they call that today, is not what Socrates would have agreed would have been Socratic or Aristotelian, because it has the false antecedent and false consequent, and calls them and says there's ex falso quod libe. I don't agree with that at all. I think material implication is flawed, and that if it's just a matter of when we say that either the antecedent is true or the consequent is true, has that does not have a truth value. So anyways, so Boole, though, otherwise was most familiar for the algebraization of classical symbolic logic and the ability to just represent things as symbols. And the value that we say has one of either two values, true or false, in the computer programming, or the value of a bit is 0 or 1. It's called Boolean, and it's Boolean in its logic, but it's not necessarily so attached to what they call classical logic today, because today what we call real logic would be more like the relevance logics, the logics of refutations, and otherwise what runs out that you always have to run out both branches of any alternatives and consequence, because only one or the other may seem to be vacuously not false, but really it just means uncontested and thus not known its firmity at all. So that's just to point out, though, that De Morgan came up with all his rules, inference rules, and they all hold pretty great. I mean, these are causalities rules, and when you associate a cause with an effect, or an antecedent with a consequent, and then also the contrapositive. When you work that backwards, the negation carries and is transitive and this kind of stuff. So De Morgan's rules are great, but after Boole and Alfred North Whitehead, after Russell and all that kind of stuff, and the whole turn of classical logic to make things simple after class set distinction and to and so Russell can sink Frege while poo-pooing that he is regularity isn't non-hypocritical, makes it so that it's just something I would hope to relay. That otherwise the tremendous success of Boole's and De Morgan's symbolic logic. Otherwise, it's to be let out that most of the things you would think of as commonsensical have a few things that aren't, that then are called the paradoxes of material implication. And instead we have what are called our modal logics or relevance logics or logic of these refutations that is much more what you expect to be not just matters of common sense, but having worked out all the different things that make it so and like it so. From this fairly basic example, Boole moved on more complex analyses, culminating in an entire chapter on Spinoza and the early modern British philosopher Samuel Clock. Boole's religious idealism helps to explain. Well, and he came up with the usual kind of silly assignments of variables to things, and then showing how he could prove things via the manipulation of algebraic variables symbolically, which is great, but otherwise there's something to be said why there's reasons to reject Boole's foundations while still having truth-valued semantics and truth-functional logic, as it were. It's kind of like logical positivism. Neither, but a strong logical positivism gets above that and is true. Boole undermined both Clark and Spinoza. All right. Yeah, he basically he says he got into nothing in something, and then he chose the one that says you can't prove anything at the singularity at the end or whatever. Instead it said it must be a multiplicity or something like that. So I won't speak too much more about that right now, but just let it be so that modern classical logic is not classical, and somehow that in some senses it's not logic. As long as you avoid material implication, no worries. As long as you avoid for direct implication, of course, is sound and profound and ... Again, this is where these days sometimes they have motions of entailment and modality and the monotone in the logic, which means that it must add up and it can never contradict itself and ... And that entailment is like, well, this is also true. That a lot of times these things are framing things that just make it easy to compute, but they're not. That's garbage in, garbage out is what I'm saying. Garbage in, garbage out is this notion of computer programs. It's like, well, I have a computer program, so it must do everything perfectly. It's got a program. It's well defined, all its actions and activities and everything that in accord so is entailed. But garbage in, garbage out means that if you put in garbage, you're going to get out garbage. And so here there's a usual notion that the actual formal guarantees of what is classical logic involve that you should know that there can't be a false antecedent proving or implying any kind of consequent, and similarly you can't say that you have a false consequent, otherwise it's vacuous way. I will reject that, and I can prove anything that I want to prove without it, with these relevance logics they call it, or these days, and super classical logic, paleoclassical, postmodern logic. So that's something that is pretty profound usually for these people. And, the discoveries and opinions of Galileo. What is this about? Well, Galileo is famous before Newton as the classical laws that go into what makes Newton, and then Newton has the calculus, so he also has his dynamical settings about what makes it so that it's there's a calculus for it, and the discoverers or inventors of the calculus. And then you have the system of the world, and I got this. I really enjoyed Kepler's epitome of the motions of planets and stuff like that. And some of it is kind of fanciful, and even a bit farcical. But Kepler is great, and I really enjoyed reading him. So Galileo's got a lot going on, and part of it is like objects fall in motion together, and then there's also stuff like infinite sets are. There are as many squares as integers because there's infinitely many of them, and Galileo delighted. While Newton spent much of his life in alchemical pursuits and theological speculations, Galileo, almost alone in his age, ridiculed the alchemists and ventured into theology only when it encroached upon his science. Theology is super scientific. Copernicus, Galileo, Kurzgesagt. I should not have expected such carping criticism as this, for the word infinite in place of the phrase extremely large is a way of talking that is used every day. Then here there's the idea that there really is one, there really is an infinite, and because we can say instead of infinite, infinitely large, that we're just kind of small, and then there's the beginning and the end, and then we just are in the middle. So this is the middle of nowhere, because otherwise inductive inference makes neither end available to the other, but they both exist, or else one of them doesn't. So again, this is why then we otherwise have to take all the arguments that would reject that, because it's intractable fundamentally. Eventually, according to induction, at some point in time it's not tractable to any finite for each finite thing, that is still so that it exists and we can attain to it. So that's kind of thing that goes into that. I did not mean to spend so many words on this trifling, Your Excellency, but since the more has been done, the less remains to do. Now for this other charge of violating the laws of logic. Giudici, in his discussions of the telescope, said that to have included an effect which does not exist or to have left out one that should be given. That's the basic idea then, that well, if we have a continuum mechanics, then that should be about it. Illumination, studying, light and Fresnel and this kind of stuff. There's Goethe, and Goethe came up with this theory of understanding and perception and this kind of stuff, and then he attaches some kind of scientific and pseudo-scientific notions to his theory of color, and it's kind of like Boole in that sense. Yeah, at the same time, it's nice to have kind of a means of talking about the apperception of things, but we just frame all that stuff in terms of the phenomenological and the noumenalogical. What's this here? Oh, and then this is the crime of Galileo. What does it say? This is just. I haven't read all this yet, but it talks about certain of his confreres. The skies themselves seem not to leave the issue in peace. We'll come back to something like that later. This is more of just kind of like the story of the church and the Spanish Inquisition and Torquemada, which is terrible, and then the Roman Inquisition and Galileo and Galileo's banishment, but to his home, where he continued to write his thing. Well, at the same time, Descartes kind of got a free pass because he was Jesuitical and this kind of stuff in the time, And then here's, of course, his boundary value problems, and this is about as far as we've got in terms of wanting to discover and discuss the Fourier analysis and the Fourier-style analysis. And then this harkens back to the earlier talks about, like, how about an inverted hat analysis that's kind of similar, making for these other completions. If you can figure out these other completions and forms that attain to these things, and then figure out analytically how you can find closed forms for them as they go to it, or numerical methods that figure out initial segments and arrive at continually improving approximations, and particularly in where it's possible to so analyze and determine the bounds of the error term associated with any approximation, there's an error term, then this is the idea that there are lots of different types of analysis that can provide quantitative fact, and that Fourier analysis is definitely among the most famous of them, because it's built with sine and cosine, or the otherwise readily available and familiar trigonometric functions, and some certain properties of them about orthogonality and the linearizability of the small angle approximation of sine theta, as sine theta over theta equals 1, sine goes to 0 or such, or as x goes to 0. These are very particular properties that then these days also has the entire world of wavelet analysis, and then these kernels of in the centers of these analytical regions of the windowing and boxing that provides, given inside these bounds, the necessary guarantees that the analytical character of the mensuration is true. Has also the wavelet analysis and wavelet transforms after Fourier analysis on Fourier transforms, and for Mellin and Hankel and Z transforms, or for any system of orthogonal functions that you can carry out the same kind of analysis and arrive at some same kind of set of results. That this is where we got up to basically whether there was a discussion of heat and the usual notion of continuous quantities and continuously changing quantities, then insofar and as to whether there's a higher order resonances or that could result heat bubbles, or the magmas, or the magmatic, and this kind of thing, with regards to otherwise the linear impulse is the entire linear impulse. Now, this is to say that we generally have a notion of cause and effect and equal and opposite reactions of the perfectly inelastic collisions as what results for non-deformable surfaces, all such manners of the inputs and outputs, what result conserved quantities and energy, force equals mass times acceleration. So that is not necessarily sufficient, because we have that somehow that pans out in the sense of in projection and perspective, that it has an area effect, and it's not just the point impulse or the linear impulse, because that's explanatory for the kinematic and kinetic, and the linear and rotational explain how the things are different, whereas they all only deal in terms of quantity of energy, but there are many forms of energy, and it all deals with the classical quantities and the measurements, but it ends up over time that everything is according to potential. The potential fields are the real fields. So talks about convection, and there's much to be said for this. 1 over A, Qx and Kx, defined constant. The existence of a steady state solution for a type of parabolic boundary value problems. Institute, International Journal of Math, Educational Science and Technology, 1988. Sturm-Liouville. Sturm-Liouville provides a bunch of conditions where something's integrable, or that there exist solutions for it. Historical epilogue. Sturm and Liouville, who had become friends in the late 1820s and remained friends for life, went on to have distinguished careers. Sturm, who had changed to mathematics from early interest in fluids, had to overcome the difficulties being a foreigner in Paris and a Protestant, but could always count on the support of Liouville. Sturm and Liouville. Liouville succeeded Sturm in his chair. He developed a new mathematical interest in analytical number theory, resting the Sénadier de Montparnasse thanks to his wife. Verify that if px equals sine x, then the Sturm-Liouville problem, px prime quantity prime plus gamma x equals 0 on 0 pi, which has no endpoint conditions, has an eigenvalue lambda equals 0 and find two linearly independent eigenfunctions. They cross and they form a vector basis. Daniel Bernoulli. The Bernoullis, of course, are famous for many things. Counting arguments, flows, many things. Perhaps there was an element of irritation in the fact that Euler now stated what Bernoulli had known for some time. Oh, that Euler. Euler is usually the one, and especially Gauss, he's like, I wrote that down 30 years ago. The Rees-Fisher theorem. All right. There's much to be gotten into in terms of this. This is usual requisite material to get into, and it takes a while. The cooling of the sphere. In 11.1, 11.6, we posed some heat problems, but in asking for a steady state solution, we actually posed boundary value problems for the Laplace equation. So that gets in the Laplacian, that the second partials, sum of the second partials equals 0, or how that gets into it. And there was talk here in the previous talks about like the anharmonic, and maybe potential theory isn't just the theory of harmonic functions. Talking about Dirichlet and then Poincaré and Euclid's smooth plane and Poincaré's rough plane, in terms of whether the continuous is really just always on the ridge or always off the ridge. Trying to figure out how those are the same kind of things. The Poisson equation on a sphere. Poisson, again, famous for both continuous mode things and discrete mode things, like the Poisson distribution and the expected arrival time of events. There's a bunch of different distributions named for people or named for their parameters, like Poisson distribution, or the normal distribution, Gaussian distribution, and this kind of stuff, or beta, or the hypergeometric, and Weibull, excuse me, and the logistic equation and this kind of stuff, and Erlang and such, networking and queuing theory and the expectations of these in probability theory. Here's a picture of Hadamard. Here's a picture of Hadamard. There he is. Heaviside function, not a real function. Heaviside function is a step function, meaning a curve arrives from one side at 0. It steps 1, then it continues. And so the problem is that in the notion of that function theory, whether or not you can have an asymptote, the vertical line. And it was mainly considered a real function. Then in this book and in our discussion, we already considered a little bit like, well, what does it mean at the endpoints? What is the value, and is it the middle, or is it either end? So there's a usual notion that you can build it either way, but the fact goes that you still have to build it one way to get through the middle. So that gets into all these kinds of things that are necessary for a proper foundation to support these things without ending up contradicting itself when later, high up above in it, are built these same models of these things that fundamentally and utterly would contradict each other. So that's one of the reasons why this square Cantor space and these notions of the modern foundations that arrive at these things that make it so possible for there to be a consistent theory overall are the needful for theory writ large and these kinds of things. Uniform convergence, absolutely uniform convergence. Counterexamples in convergence. So that was that stack. And then, of course, this is what we've been reading, is differential geometry, symmetry, submersions, and sheaves here, going up to that. And Parmenides here, this is about Heidegger then in his translations. So why is Heidegger famous? Well, because he made popularizations and translations of the ancient Greeks. About the notion that we usually have of knowing something is that it is there, and then he mostly helps explain that the ancient Greek notion of lethe is don't know, and so alethe is in a dialectic is to uncover these things, to reveal these things that exist. So that makes more for this strong Platonist universe that they do, and they come together, and that's what everybody would arrive at. Anybody could arrive at. There's no road, there's no royal road to geometry, you might say. It has its own though, so if you're going to get there, you will find it. You know, this kind of thing. So there's that, and then what was this? Here's Courant. Yeah, this is so. These the differential integral calculus of Courant. Volume 1 and Volume 2, here I got this, and what is it? I got this at a book fair. It only cost me not very much. Inner Science Publishers, 1933, reprinted in 1959, so these are 1959 editions. And he gets into like the usual notions of all the needful to have about a theory of real analysis, and to get into the notions of the integral and differential analysis. Further remarks on the connection between the integral and the derivative. The usual notion of a derivative and the integral is that they're functions. So for a given function, if it's differentiable, it has another function called its derivative, and if it's integrable, it has another function called its antiderivative, or integral. And so, before we begin to follow up the relationships found in section 4, systematically we shall illustrate them from another point of view, which is closely related to the intuitive idea of density and to other physical concepts. So he starts talking about mass distribution and density, total quantity and specific quantity, same relations, assumed differentiability, specific heat, question of applications. Anyways, largely the Courant is pretty great, and it's modern. Pretty much anything you can find in the Courant is pretty much held up in its textbook today still too. So after when I was studying the university text, they're kind of like the older school, and after the infinitesimal analysis and the like Price or something like that from 1900, which is this massive tome on analysis, and so the stuff that came up about the integral equations and their plane curves and stuff like that, you can kind of point to Courant as having put up what ends up being the side that makes it so that in the linear narrative and the linear curriculum, people come up with a mathematics degree these days prepared to set their differential equations up for linear eigensystems that end up being crunchable. Unfortunately, there's some things that end up just not being tractable to that have plain, ready, and apparent solutions in the integral equations. That's one reason I really got in this identity dimension for the linear fractional transform and D'Alembert and these kinds of things that it really deserve a lot more to go into them to figure out why those kinds of singularities in the singularity theory are the envelopes vis-a-vis the asymptotes. So I leafed through volume 1, and I really did enjoy it. Here, formulation of the concept of function. See, for our function theory, it gets into all these kinds of things. Tangents to graphs, about the increasing and decreasing, and how those are same and different, where they project and whether either one has the abscissa and the ordinate on either side. And how, for example, you might be able to frame those in an identity dimension and have those fall to both sides, the x and y, and figure out what happens when a parameter is recursive in itself, that if a differential function is a function defined in terms of its own rate of change, then you think of this own variable defined in terms of whether it changes. That's a pretty fundamental thing, helping to explain why the identity dimension and so far as that goes in this complex diagram, as an example, is pretty fundamental and is advisory to something like the meromorphic, or otherwise notions of about how to implement free analysis on the plane or other surfaces when otherwise they would just quit. So, anyways, these Courant books are great, and you can rely on them. They're not complete and replete, but they do have a quite good setup of the complete and usual linear narrative, the usual complete order field. There are other models of real numbers that suffice to be continuous domains. That reminds me of this book I found that it's called Topology via Logic. And so topology and function theory are, as mentioned here, kind of the two things that have varied the most in terms of definitional dynamics over the course of the thing. And so the definitional dynamics kind of set up to what is a function and what is a topology. And the usual notion that we have in our linear narrative and curriculum, of course, is least upper bound property, measure 1.0, and an open topology. So what is arrived at is that there's, in this topology via logic, is that it's set up with these notions of Boolean lattices, and there's Dana Scott. So Dana Scott, he's a Californian, and he, for example, would be able to tell you the difference between classical logic and these relevance logics. And he has his own notions of how to get around what is otherwise this bulwark of, you can't contradict the tower, the ivory tower, which is different than the symbol of the tower as the Godhead or something like that, which is a different kind of talk. But so anyway, Scott, Dana Scott, he is going to be more utterly famous because he's set up a lot of these inroads into putting the classical and then this relevance logic or the things that go into making these back together. And that includes that he talks about other topologies than the usual open topology and about building that up without necessarily otherwise having to share these same fundaments, as you would see, that he would be unable to not derive a contradiction, which I do from just coming up from the entire thing over one theory of everything. That the topology via logic is a pretty great little book, and it helps illustrate that there are other continuous domains, and that basically gets in the whole notion of category theory and what is a continuous domain at all, and how that could possibly be when all our theory has is continuous functions otherwise, and some properties are real numbers and this and that. So anyways, topology via logic is a pretty great little tome, and it was only printed in like the 70s or 80s or 90s. But that's because we have this whole formal apparatus of the linear curriculum of the standard narrative, which is great, and it has its inductive completions about how to put that back together with the wider world of the deductive inference and the deductive completions of these other things which are true, and helping to explain uniform motion and infinite divisibility and these other things which otherwise can be seen to make contradictions and paradoxes and otherwise the plain theory. So, let's see. Heidegger. So this is about Heidegger, and he translates Aristotle. He translates, this is Gadamer, and Gadamer is pretty cool. Gadamer was Heidegger's student, and he's talking about Plato. He's talking about his Festschrift, or his 70-year anniversary, or whatever it is. Dilthey, the Weltanschauung. Now, I'm a big fan of the Weltanschauung and the Anschauung, but some of this other stuff gets attached to material things that aren't so much relevant. Kierkegaard, Heidegger, Buber, and Barth. So this is a brief book, and its original title, it says a study of subjectivity and objectivity and existentialist thought, but its original title was something like it's very ambitious, Let's see what it says. Anyways, it was like all theory or something like that, or theology, in the modern world. So this is pretty good. James Brown. Not the usual James Brown you're familiar with from popular culture, who's so famous, but somebody who's talking about the subject-object distinction and objectivity. And Here he quotes Wilkie Collins from The Moonstone, 1868. This question has two sides, he said. An objective side and a subjective side. Which are we to take? He had had a German education as well as a French, the original English foundation showing through every now and then. Take the objective view first. What do we know? Do you mean to deny the objective view so far? Very well then. Now arguing this way, from within outwards, what do you reach? We reach the subjective view. I defy you to controvert the subjective view. Well, very well then, what follows? The objective subjective explanation follows, of course. Objectivism is and subjectivism are kind of like entropy, and there are various readings of the way that they're reversed. And it's kind of like similarly with this logic and entailment and the monotonicity. There are ways to see it both ways, either way, and then that really sorts of makes it so that either way by itself is missing out. So, anyways, this is pretty enjoyable, and it's just another thing that you can sort of cite as a source of authority in terms of bibliography reference, because the path to our ivory tower is a stack of books. It's these giants that we climb on their shoulders. They're made out of books, bibliographic reference, the silver thread, eternal braid, this kind of stuff. What is this? So Badiou, he's supposed to be the next being an event, but really that's just, I'm not putting too much into that, because being an event is, it's just, the event is particle wave duality here already. So trying to frame it down as another linear impulse stacked on the top of a world of linear impulses to get back down is just hypocritical, or it's wallpapering, I call it. You got your coattailing riding up, and then when that starts to get bad, they just wallpaper it on down. I just want to relay that for what it is, there are already things that do it, and for what it isn't, it doesn't say anything either. So. There's one of these books of Bohm. Unfolding Meaning. Weekend of Dialogue with David Bohm. Here's a picture of him. This is not so much relative to the meaning and the quantum consciousness and these kinds of things that it gets into, but when it comes otherwise to quantum theory and the real wave function and the Schrodinger picture and the Heisenberg picture and stuff like that, Bohm de Broglie these days is standing way up as much better advised for that. There was a 40 or 50 year period where it was a footnote and poo-pooed, but now the people who kind of relied on that are having to find themselves, scratch themselves out. So, if they even don't care. Well, we're coming up on time here pretty well. This was this epitome of Copernican astronomy and the harmonies of the world. So I guess it's called the harmonies, pretty much. It's about the musical spheres, and it's written like in the 14 or 1500s, right? When was this? When Kepler was around. So Kepler and Tycho Brahe were famous. So it says 1611, 1609, and Kepler, Graz, diversity of opposite parts of the same body. How do the planets make their circles and ellipses, What were the immobile celestial spheres? How does all this geometry add up? Kepler frames it, he makes question and answer sections. So he'll pose a question, a hypothetical, a rhetorical question, and then he'll answer it. What does that mean? Well, it's easy to read because he kind of sets you up to expect an answer, and then you provide one. So it's kind of a rhetorical method and a rhetorical device. Makes for easy reading. Well, there's that. And then I picked up this copy. Now, this is something a little bit more modern. What does it call it? Radar and sonar. So radar and sonar are two complementary things. Kind of like the maser is the microwave laser, but it was invented first. Before there was the laser, light amplified by the stimulation and emission of radiation, there was a maser, microwave amplified by the stimulation of emission of radiation. Masers. So anyways, then there's radar and sonar. So this gets into the acoustic and the and Doppler and the notions of reflection and signal and information theory writ large. And so this gets into a lot of different things that explain not just the mathematics that go into the classical things that would reflect notions like the source and image and focus and that kind of stuff, but also the practical things that end up kind of like Gibbs and the ringing phenomenon and stuff like that, about how radar and sonar work. And these are the theories. This was a penny to get this book, pretty penny. And the ambiguity function, synthetic aperture radar, and these fundamentals that go into designing and finding how those things are. Well, anyways, we haven't talked about much these days, just kind of looking at some books. But what it is about it, from the stop derivative is a thing, and it's relevant to classical motion, and it's relevant for Einstein's attack on Newton's attack on Galileo's classical motion, and putting those together. And so it's going to be a real thing. And then the ideas of otherwise, these universals and the theories and stuff, that's just pretty regular. Right? And it's something about, well, really, you can take it or leave it. And then if there's anything else, I suppose I didn't wind the clock today, It's always a matter of time, how these things go. And now that clock will run a bit. It'll carry on. And well, it's 2023, coming to close. Season's greetings. So long. Good luck. Goodbye.